So picking back up where we left off from the last video, we were considering the function y, f of x equals the square root of x, the graph of the equation, point satisfying y equals the square root of x. You get the idea. And we were zeroing in on a point with x coordinate 4, y coordinate 2 that lives on that graph. We were trying to find an equation for what we called a tangent line to that graph. If you don't remember this, did you watch the videos out of order? I mean, go back and watch part 1. Anyway, so we've got our point. We needed the slope of the tangent line, and we used a limiting process that we'll lay out more carefully in just a second. We've already, again, part 1, we did it. So it looks like through that limit process of sort of taking approximate secant lines and trying to get close to the tangent line, our tangent line slope, again m with a subscripted tan for tangent, So we found that for a given value of x, like I said, I plugged in a placeholder x, a variable, like you use variables for, to point out what's going on. So we didn't have to do this again. If I said, aha, well, what happens at x equals 1, or what happens at x equals 10? You get the idea. So with an x coordinate of 4, we can plug that in there. 1 over 2 times the square root of 4. Hopefully you don't need me to do the arithmetic for you to say that tangent line slope is in fact 1/4. So our equation, we have y minus our y coordinate. So y minus 2 equals 1/4 times x minus our x coordinate, x minus 4. And if you rearrange this into the classic slope-intercept form, you should end up getting y equals 1/4 x plus 1. So there you go. So that's an answer. That's an answer to the question of what would an equation for the tangent line be. I didn't quite want to leave that hanging. We'll take a look at another example of this in just a moment, but I really do want to dig in and look at that structure we use to evaluate, this tangent line slope in the first place. Need a moment. All right, so our formula is back up here. I've gone ahead and generalized it a bit because I'm a math teacher. That's what I do. So instead of square root here, I'm just putting in f of these quantities. So we have the function evaluated at this x plus h spot that was just bumped a little bit off our target point x, minus f of x. Whole thing divided by h. Again, this format you may recall from some homework exercises. You may have seen it in a course previously referred to as a difference quotient. That's fine. Anyway, and we ended up seeing that for a particular value of x, that would give us our tangent line slope. Now you may be wondering, Professor Carroll, why did you write the m sub tan over here? Wouldn't you normally do it over there? I would, but I want to put something else there because as it turns out, this particular notion comes up often enough that we've given it its own name and its own symbols. So for for a big chunk of the remainder of this course, we're going to talk about, something where I'll just refer to this as f prime of x. So that, looks kind of like an apostrophe, but not really. So I'll read that as f prime of x equals the limit as h approaches 0, f of x plus h minus f of x all over h. So we call that the derivative of our original function f of x. Whoa. Did you feel that? It's like the earth just moved underneath me. Okay, all jokes aside. No, this is a really, really foundational concept of calculus, this notion of a derivative. We'll look at it more from a kind of a different perspective in the next section. But for now, knowing that this is the derivative that we're calculating when we evaluate this limit of this difference quotient thing is, going to drive a lot of what we do in the remainder of this section. Now, I also want to point out This is the most common notation you're going to see in Math 115. I try to be consistent just so nobody gets confused. But there are some other ways you will see a function's derivative denoted. If you go poking around, if you look in our textbook, you'll see some of these things as well. So you'll sometimes see this is often referred to as Leibniz notation for a derivative after the guy that was doing this geometric stuff. So df over dx. It's not really a fraction. Don't try to do any division based on these things. Yeah, again, it's just notation. But you'll sometimes just see d over dx written in front of something to indicate a derivative. You'll also see from time to time what you might hear called an operator notation, where you have a capital D to represent derivative of whatever the function is sitting in the back. The little subscripted x tells you that it's a derivative with respect to the variable x. So I just wanted to give you all of those notations. All right. So now that we've got this thing in place and we have this limit definition for a derivative setup, let's take a look at it in the context of another example. The good news is it's going to be a bit less complicated than the last one. Like I said, easier than having to work with square roots. We won't have to rationalize anything here. So the function is just a relatively placid quadratic x squared plus x. So let's get a formula for the derivative of this thing, and then we'll use it in a tangent line calculation momentarily. So g prime of x, we've said, is going to be the limit as h peters away to 0 of g of x plus h minus g of x all over h. All right, now I've got to take this in sort of two stages. I'm going to feed this x plus h in here, and I'm going to have to pound out some algebra. Then, I kind of just copy and paste that formula in place of g of x. Anyway, I'll try not to skip too many steps here, even though I am kind of short on board space. Anyway, so x plus h squared plus x plus h. Again, that's just coming from me feeding that in here. Haven't worked out any algebra just yet. Minus all over h. You'll notice I tend to be really picky about my notation here in the course of these videos and with web work, not having to a lot of show your work type stuff. You'll notice I tend to be very careful about writing limits out in front of all these things. I try to keep stuff over that h rather than just doing a whole bunch of algebra off to the side and then, spontaneously generating a denominator, underneath it, that sort of thing. Anyway. So now, we've got to expand this stuff. X plus h quantity squared. Feel free to pause if you want to FOIL this or use, your grid or, however you want to do it. But when I work that out, I get that guy. X squared plus 2xh plus h squared plus x plus h. And I don't really need the parentheses there. Remember to distribute this, subtraction here. Both of these terms are going to change signs. In the grand scheme of things, I'd say that's probably the number one algebra type mistake I see calculus students make is failing to distribute a minus. They just write minus x squared plus x, and then that's gonna screw everything up, for lack of a better way to put it. Now at this point, that's a lot of stuff. You're probably hoping, gosh, I really hope some of this stuff cancels out, and you can probably already see that some of it does. So we have the x squared minus the x squared, they're gone. We have the minus x, and we've got this plus x sitting right in the middle. Now, at this point, you might be saying that's still pretty ugly, but it's going to get less ugly in just a sec, because if you take a look at the three remaining terms in the top of this fraction, we have a plus h squared, plus 2xh. We don't really need whichever the plus for whichever terms in the front, but all of those have what in common? Exactly, they've got an h in common, which means we can kind of factor that guy off. So you ever just wanted your board to be like 6 inches deeper? Anyway, so if we factor an h off here, factoring an h off that gives me a 2x. Factoring an h off here just gives me an h. Factoring an h off that guy, it's not a 0 because it's like a multiplication division deal. It's a 1 all over h. And just like we saw back in chapter 1 when we're dealing with limits, anywhere other than 0, we're good to cancel away this factor of h. So they're gone. Now, there's no reason we couldn't just do a direct substitution of 0 in for, be very careful on this front. Where should you plug in the 0? You're plugging it in for h. This is a limit as h goes to 0. I mean, it's easy to overlook that, but be very careful with it. So you end up getting a derivative value of 2x plus 1 here. So now give me just a second. I need to clear some space, and we'll talk about it, how this looks for the tangent line. Okay, so we have a formula for our derivative. So this isn't like by itself our tangent line slope. Please don't go shoving this thing into the those line equations. This you're not going to get an equation for a line. But so if at a particular point, so say 1, 2, our x coordinate would be 1. So our tangent line slope is, I think I call this g. So g prime of 1. So now we can plug that 1 in here and get a numerical slope back. And hopefully you can tell that 2 times 1 plus 1, that gives me 3. So if we wanted an equation, I didn't actually close any of those. So if we want an equation for this line, y minus 2 equals 3 times the quantity x minus 1, or y equals 3x minus 1 after you distribute the 3 and then add the 2 over. So, all right, so we got our slope, we got an equation for our line. Awesome. So I want to do a couple more examples of this, how we calculate derivatives before we change gears and look at it from a different direction. Hopefully you'll see why when you watch the next video.